Hello, everybody. Welcome to TWSS 2021, our final day of this presentation series. Our first talk of the day is going to be by Dr. Andy Yu, talking about using VSim to explore the design of a plasma-filled W-band TWT. And on that note, Andy, I will pass it over to you.
All right, great. Let's start then.
Welcome.
Thank you. So then in this presentation, we will explore the modeling of a cutting-edge plasma-filled traveling wave tube that's currently being researched by Dr. VSim and his team at the Central Electronics Engineering Research Institute of India, and answer the question, how can I use VSims to design and model complex electron devices that involves unconventional physics, such as the plasma process? And perhaps more importantly, why do I want to choose VSim over other products? My name is Andy. I completed my PhD in May of 2021, that's this year, and joined TechX as an applications engineer in June of 2021. My PhD specialization is in vacuum electron device simulation and analysis, especially of cavity magnetrons. I also have formal educations in areas listed here. A couple notes before we start. The TWT simulation project to be discussed here is part of Dr. VSim's research. Dr. VSim is a TechX client, and he has generously granted limited permission for this presentation. Since the simulation is part of an ongoing research that has not been published, aspects of the presentation setup and results shown in the following presentation are not optimized. TechX respects and protects the confidentiality of its clients and their research. The primary focus of this presentation is to showcase VSim's capability rather than discussing the science of the device that has been simulated. In other words, this is more of a VSim presentation rather than a TWT presentation. The presentation is divided into 5 parts. First, I will show you how the geometry of the structure can be built natively in the VSim Composer graphical user interface. Second, I will show you how to do a mode analysis based on a single element or a single pitch of the periodic structure. Third, I will show you how to set up the input signal and the electron beam to get velocity modulation. Then I will show you how to add a plasma into the simulation and how to set up the plasma process. Finally, I will discuss why VSim is the ideal tool for doing research on a device like this. Some basic device descriptions. This is a staggered double vein slow wave structure that is designed for the W band or 75 to 110 gigahertz. This structure doesn't cover the entire W band, but it covers a significant portion of it. So it's a wideband structure. This geometry, the geometry of this slow wave structure was originally published by Lai and others. And the original publication can be found here. This figure, the figures on the slide shows a visualization of the geometry with parameters. Note that these figures are actually negatives of the actual device, so they show the vacuum portion of the structure. So now I will show you how a geometry like this can be quickly built in the VSim Composer GUI. Let me get my screen. So in VSim, when you boot into VSim under geometries, you can go to the CSG tab, which will contain all the shape primitives you can use. So in this mode, you can compose shape primitives and you can do Boolean operations on these shape primitives. That include union, intersection, and subtraction. So to build a structure like this, this structure is basically a collection of boxes that can be union or subtracted, and then this shape will be achieved. So to do that, I have already inputted all the parameters to save some time. So what can be done here is that you start with a basic box. Then you get a later box, a little box that is the part you want to cut out. And then you simply do a box 1 minus box 2. Then you have this shape with a notch in there. Then you repeat the same thing and cut out the rest. The third step, you have this. Then you cut out 2 more sections, you have the complete shape. So it's really just as simple as this. If I fill in all the elements, you can see we started with a basic box like this. Then we cut out a section, cut out another section, cut out 2 more sections. Then we have a single pitch of our periodic structure. Easily done. And what if we want to have multiple periods, or we want to add more periods or subtract periods? That can be simply done by right-clicking on this structure and click Create Array. And then all you need to do is to define the spacing between each period. In this case, it will be the value of the width of a single period along the axial direction, which I believe is pitch value. So say we want to make 5 periods of it, except then we have a 5-period structure. And you can add and subtract periods easily this way. So the geometry building is very simple for this type of geometry. And I believe we have another presentation after this exclusively on geometry manipulation. So I will go as far as this for this presentation. So now, the next thing to do is mode analysis. So mode analysis can be done based on a single element. And the purpose of doing a mode analysis is to get frequency response of this structure. So there are some very well-defined steps to do this in VSim. Usually, first you define a current source that contains multiple frequencies and add it to the simulation to excite the structure. Then a periodic boundary condition can be defined in the axial direction. That is the direction along the periodicity of the structure. Then you need to give it enough time to allow the simulation to run sufficiently long or till you get some sort of close to some kind of steady state, which is frequency dependent. In this case, since the frequency is very high, you don't need to run it for as long. And then what you end up with is the electric field profile that contains the modes of the structure. And these modes can be computed by using a VSim analyzer called extract modes via operator. So I will show you how it's set up just briefly. Let's get rid of this. Since we're doing a single pitch. So here is the driving signal here, which is a very simple function. So this is the driving signal that is inserted into the simulation. And the way you insert it is in current distribution, you define a general distributive current, and this current can be artificially insert into the center of the structure. Then if you observe this function, you define a lower bound of the frequency, then you define a higher bound of frequency, then you define the frequency delta. That is how big you want each frequency step to be. And this function is pretty well known. So afterwards, when you run this simulation, also periodic boundary conditions are in basic settings. In this case, periodic direction is periodic in X, which is along the axial direction. And after running the simulation, you can run the analyzer, which is here, extract mode via operator, and here are the complete direction on how you can run this analyzer. And also the content of this analyzer is can be found in a Python file. If you can read Python, you can actually go directly into the original Python file and see what the function is actually doing. Alternatively, you can read this paper, which is published by TechX people, to talk about how this analyzer extracts modes and why it's reliable. So after you run the analyzer, you have output like this. Usually you have a real frequency and you have an imaginary component. That's just a numerical thing. That's all the parameters that satisfies the algorithm. But usually we want to select frequencies real components when the imaginary component of the frequency is very small or near zero. So in this case, since we're looking at the W band, we can clearly see there's a mode at 84 gigahertz. There's a mode, these are very large. There's a mode at around 91, around 95, around 110, around 103. So these are the modes, are the frequency response of the periodic structure based on a single element. Can be very quickly done in VSim. And the next thing is to show velocity modulation. So there are several things to be done here. The first thing is we need to have an input signal into the structure. And then we need to set up a wave absorber as the output. So this type of simulation, whatever goes into it, have to exit somehow or being absorbed somehow. And then we need to set up the electron beam. Then we need to add an external magnetic field. And the last thing is to add some diagnostics of the quantities we want to see. So I will show you how to do that. Rather, I will pull out this screen here. So, okay, let's start here. So first of all, let me explain where we are. So we just built the geometry in this case, I repeated the periodic structure 30 times. So there are 30 pitches. This is not the original design. The original design have 80 pitches, but for the sake of demonstration, I'm only doing 30. And also, if you notice, this periodic structure is also embedded in a waveguide. So if I get rid of the structure, you can see here is a waveguide. Let me make it larger. Here is a waveguide. When you add in the structure, you'll have basically the basic bulk of the TWT. And the reason why the tail end is much longer is because it's going to be filled by a wave absorber to absorb the output. So what do we do now? So this is basically where we are. There are no other settings. So everything under field dynamics, this is what you are going to have when you are just booting up a brand new VSim simulation. And here I have some history set up already. And this histories we will talk about slightly later. Let's talk about inputs first. Actually, let's start with the most. Let's start with the easiest thing. The easiest thing is to add the external magnetic field into the simulation. So in this case, the magnetic field direction is obviously in X. So to do that, you simply go to field dynamics, go to fields, right-click on fields, add field, and say external field. Then it has this default name. We can change that to applied B. And then if we look at what we can put into this, we can select what type of field it is. It can be magnetic, electric, or current, but note whatever you put into here is applied to the entire simulation domain. You can make that not the case by having masking functions on the components. But in this case, since we are having a uniform magnetic field in the X direction, all we need to deal with is component 0. And let's give it something like 1 Tesla. And component 1 and 2. By the way, component 0 is X, component 1 is Y, 2 is Z. And this field is not time dependent. So that's all we need to do to add the magnetic field. And the next thing is that we need to be able to launch a wave into this input port, which is right here. So the way you do that is also very simple. The nice thing about this model is that this input port is right on the lower X boundary. So to do that, and also it's a waveguide port. So to do that, you add a boundary condition right here, field boundary conditions. Add field boundary condition. And there are all of those boundary conditions that are available. And in this case, if you look, the very last one is a rectangular waveguide. So let's call that RF input. And the frequency, let's give it something artificial in the range. Let's call it, just give it 100 gigahertz. Voltage, 2 volts. Start time, 0 starting from the beginning. Stop time, let's call it 1 second, which is eternity for this. And the turn on time, let's give it, say, half of a nanosecond. It is launching from the lower X, and it's polarizing in Y, which is in this direction here, polarizing in Y, and then you set up your center coordinates, like where your waveguide is centered. If your waveguide is off the axis, you will need to do a shift. In this case, I already have parameters defined very conveniently. So in this case, it's center Y and center Z. And if we look at what they are, center Y is the center point of this waveguide, and center Z is the center point in Z. And then you need to tell it what's the width and the height of this opening is, which I have also have parameters for already, but alternatively, there are a list of waveguides that's commonly used that you can choose from. But if your waveguide is none of those, you can simply put in your own parameters here. And then you have a wave input. Easy enough. So now let's talk about how do you put in an electron beam. The way to do that is, first of all, if you look at this input screen, there is no particles here yet. And to access particle setting, you need to go to basic settings. And here you have a list of switches for particles. Currently it's set to no particles. If we set it to include particles, now you have this new tab called particle dynamics. And in this case, for this step, we will add an electron beam first. We'll take care of the plasma part later. So we add electrons. Let's call that electrons. So now the particle is added. There are all those settings on particle weight that you can adjust. But now what we really want is an emitter. So add electron emitter. In this case, since we're emitting from a boundary, we can do a slab settable flux. And this is a boundary emitter. If you are emitting from some geometry inside of the simulation domain that is not on a boundary, what you do is a shape settable flux. In this case, if we look at what's the difference in shape settable flux, your emission surface is defined by an object. And in a slab emitter, your emission surface is simply a boundary. So that's a difference there. So let's get rid of this. So in this case, our electron beam is entering from the lower X boundary, which we're already at X lower. We can leave the emission offset as is and the physical offset as this. So there are several different emission models you can use. In this case, so the default particle weight is set as constant weight. Usually you can do variable weight as well. It's pretty accurate to do variable weight, but if you want to manage some stuff more precisely, you can do constant weight. And when you do variable weight, you see computed weight. Yeah, I guess for slab settable, you only have three choices. You have emission flux, emission current, and emission rate. I think you have more choice when you are emitting from a shape. Let's see here. Yep. So if you are doing a shape emitter, you have current density flux, child linear, which is space charge limited, Feller-Nordheim field emission, or you can do Richardson-Dushman thermionic emission. But that's only if you are emitting from a surface, which in this case, if you want to do any of these emission profiles, you can simply define a geometry object here as well. Someone mentioned there is a difference between constant and variable weight particles. Yes, there are. And usually, I will let other people explain this later, but usually a variable weight give you a bit more freedom on your emission models. If I set this to constant weight, it will not let me do some of those emission profiles, but correct. The comment was constant weight particles cannot field emit because of the lack of freedom, right? So if you want to do any of these emission models, you have to use variable weight as well. But in this case, since we are just doing a simple electron beam from a boundary, we can just do a slab flux, and we can simply do something like emission current density. In this case, the unit is in amps per meter squared, I believe. Start time 0, stop time 1, which is from beginning to the end. And current density, you can set, let's use something arbitrary, say 1,000, which is pretty big. And velocity coordinate system can be either global or local or surface. So when it's global, you are just using the global coordinate system. If you are using surface, then the coordinate system is normalized to whatever emission surface. And in that case, your direction 0 will be the direction that's perpendicular to the surface. 1 and 2 will be the two parallel directions to the surface. So in this case, we use something arbitrary, say, I use something like 18.5 e to the 7th, which is very fast. This is not an optimal, bunching velocity of this tube, but since we're just demonstrating a point, here's the velocity we use, and then we are emitting from the lower X surface. We're using computed weight. Correct. Okay, and now what we also need in this case is a masking function, because we don't want to emit from the entire lower boundary. And in this case, let's see, emission current density flux. I am missing a tab here, and I think something needs to be turned on to see it. Read as the emitter. Oh, I see. Right. There it is. So what happened there is that because I started with constant weight, when I first added the emitter, it is going with the constant weight setting. So when I change this, after I change this to variable weight, then re-add the emitter, it's counting it as a variable weight emitter. And then I will have access to this microparticle rate, which allow me to define my masking function. So in this case, what I really want is a sheet beam that's basically launching into the gap of the periodic structure. And to do that, I have to define a masking function. And in this case, the masking function is usually defined by Heaviside functions. So I think I have a function already defined as emitter mask. So if we look at what this is, let's look at what is emitter mask. It's basically a beam profile. So this is telling me I have a beam that is centered as the center of the waveguide with a height of 0.12 millimeter and a width in Z of 8 millimeter. So it's a pretty skinny beam, but it's wide. So that's my emitter setup. But as I mentioned before, whatever goes into the simulation have to exit the simulation as well. So that is true for both the particle and the field. So for the field, we need to add something at the end of the simulation to damp out the wave. In this case, what we usually use is a match absorbing layer, an MAL, and this layer absorbs wave of all frequencies, but it needs to be sufficiently thick. So in this case, I already have a thickness defined, which I believe is called LMAL. Scroll. This is a very long list of variables. But I remember it's called LMAL, and let's see if VSim, oh, I see, I can just put it in, I have to find it. LMAL right here. And let's see what LMAL is. So it's usually defined as it's usually reference to the longest wavelength you have. And in this case, 4 times the longest wavelength is used. So if you see it's about 12 and 12.6 millimeters, which is quite thick for this. But if you have an 80 period structure, then it's a much lesser portion. damping factor 0.5, and we need to tell it where it is. In this case, it's in the upper X surface. So there is our wave damper, and let's call that MAL upper X. Usually give it descriptive names. So that is our wave sink. Now we need particle sinks. So all of these, the waveguide and the periodic structure is already defined as PEC. The way you do it is when you do your geometry definition, you can tell VSim what material is a geometry. In this case, it will be this union, which is all PEC. But the fact is PEC doesn't mean it's automatically absorbs particles until you tell VSim to absorb particles there. So in this case, we will need several particle sinks. So the first particle sink, the way to define it is also in electrons. You have particle boundary conditions. And here are a lot of different ones. In this case, the tool we will be using is boundary absorb and save and cut-cell absorb and save. Boundary absorb and save is simply when you want to sink particle at a simulation boundary. In this case, since our upper X boundary is open, we'll use this condition for the upper X particle sink. Let's call that precisely that. Let's call the upper X sink. And we say it's upper X. Then this upper X simulation boundary will begin to absorb electrons and record the number of electrons that's absorbed. But when we are dealing with shapes such as the waveguide itself and the periodic structure, the setting to use is usually cut-cell absorb and save. And this is a similar to the emitters. This will allow you to input a geometry or to reference to a geometry that's saying that geometry is a particle sink. So in this case, let's have a waveguide sink. And the shape, it's a shape. And we'll have waveguide outer minus waveguide inner, which is this. So this is now a particle sink. Now we need another sink for the slow wave structure itself. And if you don't want to do it separately, you can also simply union the waveguide with the slow wave structure. Then you will only have one geometry to deal with. But sometimes there are benefits to dealing with them separately. So in this case, another one, let's call that slow wave structure sink. In this case, we put in our slow wave structure. And just for completeness, let's also define a sink as a lower X boundary. Lower X slab. So now, basically, all the simulation boundary possible, all the possible places that particles can be exiting the simulation are defined as particle sinks. So that part is complete. And the histories are already set up. In this case, I'm only recording two things. That's the input voltage into the slow wave structure and this output voltage. But there are a whole array of other things to look at. And we have pretty complete documentations on what these things are. To access those documentations, simply there's this help button. You click on those, you can pull out our documentation and you can go into the reference menu to see what everything is. But anyway, let me show you the results of this setup. We have, sorry, I'm struggling with a Zoom window. There it is. So if we run the simulation and we visualize it in the phase space by plotting the x direction on the x-axis and the velocity, the electron velocity in x in the y-axis, we can see this velocity modulation down the tube. As you can see, the amplitude is pretty small because in this case, since my electron beam is very fast, it's coupling to a minor mode, not the primary mode. And the amplification is also small consequentially, but you can see the signal is being amplified, very small, because it's a lesser mode. So anyway, that's all for this section. And let's go back to the main presentation. And the next thing is we need to add a plasma into this slow wave structure. What's the point of adding this plasma, you may ask? The goal is to use a plasma to self-focus the electron beam so that the device can function in the absence of an externally applied magnetic field. Many things can happen when you add a plasma process into a device like this, but for simplicity, the only plasma process we will be dealing with here is impact ionization. So in this case, I decided to use argon because it's relatively easy to ionize, and the plasma is introduced as a fluid. If you so choose, you can add this plasma in as particles and simulate it that way as well. And here is a list of things we will need to do for this step. So let's go through it now. Let's go with where we end up here. So first of all, we need to tell VSim that you are including a plasma process. So the way you do that is in basic settings. Here is a collisional framework. You want to change that to reactions. And now under particle dynamics, you have this whole new reaction tab with a lot of different process. In this case, we're dealing with a particle fluid problem. And the first thing we do is to add the fluid. And the way we do that is simply right-click on fluid, add neutral fluid. Now we have a neutral fluid 0. You can define its temperature, what type of fluid it is, and its volume, and its density. So in this case, we are doing argon. So we already have argon in this. Let's say it's something like 2000 Kelvin, a hot plasma. Volume, you can do a Cartesian 3D slab. In this case, you can alter these parameters to cover the entire simulation region. Then you will have a fluid that is filling the entire volume. Then the most important thing to set up is that you we want impact ionization. So we go to impact ionization and see what we all have here. So we basically have a formula of A plus B equal to yields A positive plus B plus an secondary electron. So we already know we have electron into argon. So we need to actually define the argon as a particle as well. Not the argon itself, because we already defined that, but we need to add argon ion into the simulation, and that is under charged particles. You can add it as argon ion. And we can call this argon plus. Then you will have argon ion added to the simulation. And if we look at this, we also have this E term. So this E is secondary electron. So you also need to define that separately as well. So we define another electron term, and we call that secondary E. Same setting as before. So note that we just added 2 new particle species into the simulation, and all those species needs to have their own particle sinks as well. And I will omit that part since we are low on time. So now what you can do is you can say it's electrons. Let's call this argon. You can tell VSim is electrons. So your background is argon. So your incoming is electrons. Your positive ion is argon plus. Your outgoing B is the secondary electrons, and your electrons are just electrons. Actually, your outgoing B is electrons, and your E is secondary. Just follow the order we defined it. And then you need to give it a cross-sectional, a collisional cross-section. So you can either do a constant, or you can import it as a 2-column data. There are these experimentally determined data sets available on the internet, but you will need to cite it if you use it in research. And we want this collisional process to update every time step, and we will leave it as isotropic. So that is basically all the setup we will need to do to add the plasma. It's actually quite simple. And if I show you the result of it, let me pull out the results. The result is as here. So this is the simulated result of this process. So in this case, we have our incoming electron beam in blue, and the red particles are argon positive ions, +1 ions, and the green particles are secondary electrons due to impact ionization. And also in this simulation, there's no applied magnetic field. So there's no external magnetic field. We can see this plasma process taking place in this structure. And by the end of it, basically pretty much all the primary electrons were gone, and you only have secondary electrons out. And you can see it's diverging because there's no magnetic field. So that's how you easily add in a plasma and simulate this process. But obviously, this still requires a lot of more fine tuning. Let's continue with our main presentation. So we did that part. So what do we want to do next for this research? So the next step is to optimize the technical parameters to get proper velocity modulation and the desired plasma effect. And Dr. Vachant expressed that he would also like to simulate the simulation to address the skin depth effect to get a more accurate, realistic simulation, since we're dealing with a very high frequency here. So VSim have an analyzer called Compute Cavity G that is specifically designed to aid solving problems like this. And this work is currently ongoing work. So now I will try to answer the question, why do I want to use VSim for a research like this? So first of all, VSim uniquely provides a unified simulation platform that enables EM, electromagnetics, particles, and plasma process to be modeled within the same simulation. And this is a unique capability. The VSim Composer graphical user interface enables rapid modeling of complex devices, which greatly smoothens the learning curve for using the software and greatly speed up the modeling process. So that if an engineer is using the software, the engineer can spend less time learning about the software and spend more time optimizing their designs. For more demanding power users, such as many research scientists, VSim provides a user with algorithm and data visibilities far beyond most of our competitors' product. In this regard, I personally consider VSim as radically transparent in the sense of algorithm and data visibility. Many of our algorithms behind the VSim's engine and the analyzers are already published by TechX on open academic journals. And users of VSim have full and unobstructed access to low-level inputs and are able to tweak virtually every aspect of the simulation setup. All the analyzers, such as the extract mode analyzer I showed you, you can pretty simply go into the VSim files and see and read the Python file yourself what that analyzer is doing. So there's no mystery or black boxes anywhere. And in sharp contrast, it's a standard for our competitors or commercial competitors to encapsulate their algorithms in black boxes, and users rarely have access to lower level setups that goes beyond the GUI. In simple words, VSim have no problem holding your hands and make your life easier if you are just beginning to learn the software, or when you want to do modeling pretty rapidly on some well-defined problems. On the other hand, if you are trying to push into new territories of science and scientific computation, VSim will now try to get in your way when you need to go beyond the GUI and work with low-level inputs directly, which opens the doors for many possibilities. So I believe that's the end of my presentation, and I will take any questions. We have 5 minutes left.
Very nice, Andy. Very nice.
So I do have one question. So are the inner walls of the waveguide coincide with the periodic structure edges? So that is a good question. That's a pretty specific geometry problem, and I think Ming-Che asked a question. I think he asked because he saw the inner geometry is actually sort of sticking out of the waveguide when you overlap it. And that is a geometry nuance. I didn't personally build that geometry, so I will have to look into it. What is the argon pressure? That is, I'm actually not quite sure. That's a good question. I think let's look at the argon plasma. So in this case, we don't have a direct pressure input, but we have temperature and density. And I think pressure can be derived from that, I believe. how much current is transmitted compared to emission. To access that information, you will need to set up a you'll have to set up another diagnostic. In this case, I only have input voltage versus output voltage, but if you want to access that information, you can define particle histories, and you can look at your emission current, and then you can look at your absorbed current. And if you define absorbed current both as the upper X, which is your exit, and then your lower X, which is your input port, then the difference in between will give you the ratio between transmitted and reflected, or if you compare the transmitted to emitted, you can see that too. But that diagnostic can be easily added. Any other?
I had another question that was sent to me. So how long does it take to simulate a structure like this with plasma?
With plasma present, so let's see. In this case, we didn't simulate the full structure. We simulated only 30 period. But if we look how long it took me to compute this, so my last step is at 9:55. Let's look at where my first step is. 9:35. So this simulation actually only took about 20 minutes to compute. And this is computed with 32 cores. So we have another question. Are the secondary electrons involved in new acceleration and collision as primary electrons? Do they have new weight? That's a good question. So secondary electrons are treated as a complete different species than the primary electrons, and whether their weight is different or not, depending on what type of setup you are using. If you so want, because even within the primary electrons, your weight is variable. So I think when you set up the secondary electrons, which I didn't include, oh, I don't have it in this case. In this case, secondary electrons, in this case, I have it set up as constant weight, but you can use variable weight on this, or you can make everything constant. So it's depending on the setup. But the principle there is they are treated as completely different species. So what is the grid style used of 20 minutes of 32 cores, and how many microparticles are used? Good question. So in this case, let's look at the grid definition. So in this case, we have cells X, cells Y, and cells Z. These are automatically computed. Let's look at what they are. So in Z, there are 28. In Y, it's 28 as well. So it's 28 by 28. And along the length of the tube, there are 421. So it's 28 by 28 by 421. How much does that give you? So 28 by 28 by 421, that give you about more than a quarter of a million cells. And the microparticle that is used, let's check that out. So in the particle setting, so particle per cell is 200, and the microparticle emission rate is also 200. So it's pretty, it's not necessarily what I would call coarse.
All right, any final questions? Go ahead and ask them now before we let Andy go. I will say that if you have not tried out the latest version of VSim, VSim 11, which we released in May, you can go to the TechX website at txcorp.com, which is txcorp.com, and you can go online and request a 30-day evaluation of the software. If you are a current license holder, but you would just, it's an older version and you want to test it out, same thing. We want you to see what we have now and some of the new features and really kind of experience all the improvements we've added. Any final questions before we wrap up? Our next talk coming up is going to be in 30 minutes. It's going to be Dr. Mark Durant, or no, sorry, not Dr. Sorry, excuse me. It is going to be Mark Durant, and he is going to be presenting on manipulating geometries in VSim. So if you want, you can take a brief break and come back at 10 a.m. Mountain Time, and we will have Mark. Thank you so much, everyone. We'll see you in a bit.